All right.
All right. So as I was saying last time, so for we define the multiple zeta values for K1, K2, Kr minus 1 greater than 1, and Kr greater or equal than 2. We define these numbers, zeta of K1, Kr, as this nested sum 1 over N1 to K1 times Nr to Kr. And of course, like I said, this converges slowly, it still converges, and this will define a real number. And we said last time that well, the goal was to prove, well, eventually the transcendence conjecture. And in other words, the goal was to understand polynomial relations among odd zeta values. And this was equivalent with understanding, so understanding two linear relations among multiple zeta values. So that's the thing. And we define in a small way for double zeta, right? We define the, we have seen an example. So of course, let me just mention that these are we define also the weight of which is the sum of the exponents, and the length or the depth, which is R. So these are the multiple zeta values of weight K and depth R. And we have seen a bunch of relations, right? We introduced, well, through examples, so we have introduced, so last time we introduced the Stoffel and shuffle relations. And we have seen, and maybe, well, I just said, but I didn't prove. So this time I will prove more things because last time was just an introduction, just to see examples. And we have seen from the Stoffel that zeta of 2 times zeta of 2, if we multiply this, would give us 2 zeta of 2 plus zeta of 4. So this was the Stoffel. And the shuffle, if we did the same thing, we obtained 2 zeta of 2 plus 4 times zeta of 1 3. So that was the shuffle. And let me just remind you, when the Stoffel is when we represent, so zeta of 2, we can represent this in 2 ways. So this was this sum of n1 squared n2 squared, right? But also we can write this as an iterated integral, and perhaps maybe I'll prove this. Well, the proof is quite easy, but I'll do it in a fancy way because I would like to introduce a special function. So we can write it as this iterated integral of these two forms. All right, so these are the relations, and from here, of course, if you combine the two, you will get that you'll obtain a relation here that zeta of 1 3 is 1 over 4 zeta of 4. And of course, we know the even values for the zeta function. All right. So that's what we did last time. And then we said something else as well. So we said that, well, we also by regularization, we allow that, oops, I hope. I don't know why it does that.
Yeah, I cannot see the.
Yeah. Let me just share the screen again.
Mhm.
For some reason, I don't know why. I hope we won't have this. Okay. Now, can you see the screen now, or it's?
No, it's completely black. It shows that you're sharing the screen, but I cannot see notability.
No, just give me 1 second. Oh wait, what? I don't know what's going on. Participants 0. What? Can you can hear me right from the? But I think give me 1
Yeah, I
second.
can hear you.
Let me just. Oh my.
Yeah, take your time.
Mm-hmm. All right, here we go. Still connecting. I hope it's not my VPN or anything. All right, so we have a little bit of difficulties here, but anyway. All right, so we said that we can express the zeta of 2 in these two ways. And of course, if we allow by equating these two, we can derive this, what we call this the double shuffle, right? So that's what we said. Double shuffle relation. In other words, it's just equating these two, right? These, the stuffle and the shuffle. But also, we said that if we allow, let's say, divergent values, such as, let's say, zeta of 1. So if we allow divergent values, we can have what's so-called the double shuffle regularization. So if we allow divergent values, we have what we call the double shuffle regularization. And we said that this happens when we multiply zeta of 1 and zeta of 2, right? And we can do it in these two ways. So we said we can do this by shuffle, right? So we have that this what was zeta of 1, 2 plus zeta of 2, 1 plus zeta of 3. But also if we multiply by shuffle, right? So this was 2 zeta of 1, 2 plus the zeta of 2, 1. And of course, this will allow us to get the Euler's identity, zeta of 1, 2 equals zeta of 3, right? This was Euler. We will prove this. I'll prove it, like I said, in a fancy way as well. And of course, we said last time that the conjecture, the Folkvord conjecture, was that these relations are enough. So the regularized double shuffle relations are enough to characterize all Q-linear relations among the multiple zeta values. So regularized double shuffle relations are enough to characterize all Q-linear relations among the multiple zeta values. All right. So there's a Folkvord conjecture. We don't know if these are the ones, but now, so this is what we discussed last time. And now let me consider, so we consider this ZK. So now I would like to look at the multiple zeta values of weight K. So this is the Q vector space of all, let's say, generated, so spanned by all multiple zeta values of weight k. In other words, we can write this as the following. So zk is nothing else than this guy. So k1, kr, right? And now we're wondering, the first question we're wondering as a Q vector space, what would be the dimension of this guy? So the question we would like to answer is, well, that would be amazing. What is the dimension? So what is the dimension of zk over q, right? In other words, if we want to characterize all these Q linear relations among the multiple zeta values, in fact, we would like to know the dimension of this vector space. And there is this conjecture. The answer, well, the answer is a conjecture of Zagier. So this is what we call Zagier dimension conjecture, which says that the dimension over Q of this Zk is this number d sub k. So this is like a Fibonacci type number. Actually, I can see there is a delay while I'm writing, and then it appears on the screen. But anyway, I hope this will be the words that we will encounter in this seminar. Anyway, so like I said, this d sub k is a Fibonacci type number. So let me just say, so this is defined recursively in the following way. So in fact, d sub k is defined in the following way. It's defined as, so like I said, is recursively. So d sub k is d sub k minus 2 plus d sub k minus 3, right? And now we also have that d0 is 1, d1 is 0, and d2 is 1. And of course, this comes from the power series expansion of this function, right? Of 1 minus x squared minus x cubed. So that would be the conjecture. So proving this, in fact, proving this dimension conjecture will imply the algebraic independence of all zeta values. So let me just write here. So Zagier dimension conjecture implies algebraic independence of all zeta values. But at this point, this conjecture is out of reach. It's we don't even know for let's say for D5 what happens if D5 has a value. We know it has an upper bound, and in fact there has been some progress towards this improving this conjecture. In fact, it was proven that that dk is the upper bound for the dimension, but we also want to prove that it is a lower bound as well. And we will see through some examples immediately. I will just mention multiple zeta values. What happens with this dimension conjecture for multiple zeta values in low weight, we would like to see. So now let's see. So before I even tell you more about the dimension conjecture, because there is, in fact, the book that we're more or less following wants to go towards towards proving this dimension conjecture. In fact, there will be this very deep result of Brown, which was a Hoffman conjecture, which from which it will imply the upper bound for Zagi's dimension conjecture. But anyway, at some point we'll get there. I don't want to go into it right now. All right, so let's see what happens with these Q-linear relations in small weight. So in low weight. So let's see in low weight what happens with. Okay, let me write this. So Q-linear relations in low weight. So we would like to see. So in low weight, and let's just take, for example, weight 2. So for when R equals 2, right? In weight, K equals 2, sorry, not R. K equals 2. What values do we have? And we have only zeta of 2. And thanks to Euler, this is pi squared over 6. We said that. And in fact, maybe we will prove this today. Like I said, I want to prove more things. In weight 3, we have 2 values, zeta of 1, 2, and zeta of 3. And in fact, they're equal. Again, this is thanks to Euler. 776 or something like that. And in weight 4, we have this. We have these values. So let's put them together. I hope. All right. You can still hear me, I hope.
Yes. I have a question. So
yes.
This dimension conjecture implies algebraic independence of these or theta functions, theta values. But I'm wondering if it implies irrationality of these numbers, for example, zeta 2 or zeta 3 over Q. It does not, right?
Irrationality. Well, it's much stronger than. Wait. All right. All right. So in weight 4. So we said that in weight 4 we have these values: zeta of 2, 2. What else do we have? Zeta of 1, 3. Zeta of 4. And we have a triple value as well, zeta of 1, 1, 2. And of course, zeta of 1, 1, 2, we can get this by regularization. So we know the values for each one of them. We know that these guys here, so we know that these guys are multiple rational of pi to the 4th, but we don't know about these values. Well, by regularization, so by regularization, we also we have something like this: zeta of 1, 1, 2 plus zeta of 2, 2 plus zeta of 1, 4. And this is 3 times zeta of 1, 1. And of course, again, we will get from here, because we know these values, this is again also a pi to the 4th times the rational number. So what we can see at this point is that all multiple zeta values in weight 4 are rational multiples of pi. So all MZVs in weight 4 are rational multiples of pi. Pi to the 4th, right? All right. So the situation is pretty much known. So it's, but the question is, what happens in weight 5? You'll see in weight 5 the situation gets a little bit complicated. In fact, much more complicated than you can imagine. So let's see what kind of multiple zeta values we have in weight 5. So we have a single zeta, zeta of 5, then we have zeta double, zeta 1, 4. Then what else do we have? In fact, let me just put these 2 values in red because they'll be important. Zeta of 2, 3, zeta of 3, 2. what else do we have? Zeta of 1, 1, 3. We have a triple zeta. And again, another one, zeta of 1, 2, 2. And then zeta of 2, 1, 2, right? I think these are, how many of them are there? 1, 2, 3, 4, 5, 6, 7. I think I'm forgetting one. Now, okay, so we have the zeta of 1, 1, 1, 2, right? We have a quadruple zeta. So these are 8 values here, right? So we're wondering how many of them are linearly independent. So that would be the question. If we want to answer the question about the dimension, right? If we want to answer the Zygius conjecture, in our case for D5. So, you know,
I have a question. So, in wait for here's the equation 2 zeta 1 1 2 plus zeta 2 2 plus zeta 1 4 or 1 3.
Mm-hmm.
So you 1 4.
Yes, 1 4 here.
But 1 4 isn't it of weight?
Oh,
5?
sorry. Oh, yeah, right. 1 3.
Okay. And
Yeah,
in weight 5, it seems that zeta of 4 1 is missing. And the zeta of 1 1 1 1 1 is also missing.
We don't allow those. Only yeah, those will just go away. Like,
what means go away?
yeah, because well,
the last number should be greater or equal than 2, right?
Yes, exactly.
Okay.
So because we want the convergent multiple zeta values, we don't want divergence. So
Okay.
all right. So this is 1 3 here is not 1 4 anyway. I just said I said 1 3 and I wrote 1 4. All right. So this is what happens. But see, in weight 5, the situation will get very, very complicated. So we have these 8 values here. So we would like again to understand linear relations among these 8 values. And I'm just going to write. I'm going to copy. I think just some identities, some linear relations. In fact, I will say this thing: the Q vector space Z5 is spanned by these 2 values, zeta of 2, 3, and zeta of 3, 2. In other words, all the others can be expressed in terms of these 2. And let me just write it. I'm just going to write a list of identities here. Zeta of 5. And as we go along and prove some other more general results, you will see that this will follow immediately. So zeta of 5 can be expressed as this: zeta of 4 over 5, zeta of 2, 3, plus 6 over 5, zeta of 3, 2. And of course, what we'll call later on the Drinfeld duality theorem, 1, 1, 2. Also, the zeta of 1, 4, we have this, it can be written as negative 1, 5, zeta of 2, 3, plus 1/5 zeta of 3, 2. So again, you see these, and this can be as 1 zeta of 1, 1, 3. And we also have zeta of 1, 1, 2. So the triple zeta of 1, 1, 2 is zeta of 2, 3. And zeta, the triple zeta 2, 1, 2, this is zeta of 3, 2. As you can see, all these relations, all the others can be expressed in terms of these 2. So in other words, we can say that there are 6 linearly independent relations among these 8 numbers, right? So in other words, so there are 6 linearly independent relations among these 8 numbers. In other words, this will imply that D5, if you want, is less or equal than 2, right? So we have this upper bound. But if we want, so if we want D5 to be 2, so if we force equality, well, we need something to prove something. This will be equivalent with proving that the zeta of the double zeta of 2, 3 over double zeta of 3, 2 is irrational, right? Something like this. And now the question is, well, so I can express all the others, all the other multiple zeta values in weight 5 in terms of these two. But the question is, can I express this double zeta, these two particular double zeta values, zeta of 2, 3, and zeta of 3, 2, in terms of odd zeta values and some kind of powers of pi or something like that? So that will be the question. Well, I'm gonna just state something non-trivial, and I'm not just gonna prove it. We will see it at some point in a much more general fashion. So now we're wondering if there exists some kind of a relationship between these. So the question is, can we relate zeta of double zeta 2, 3, and 3, 2 with all zeta values? Well, basically with zeta of 3 and zeta of 5. So that is a question. And the answer is yes. So I'm just going to state the linear relations. I'm not going to prove, we're not going to prove them yet. At some point, we will prove them. In fact, like I said, in a much more general fashion. But let me warn you that to derive these relations is not an easy task. In fact, you need some kind of a motivic setting to derive this relation. So as you can see, even in weight 5, we have huge problems. But first, before I even go and write down these relations, we know from the so let me remind you that from the Stoffel, we have that zeta of 2 times zeta of 3, if you want. We have a relationship between these, right? But it's not enough. So we need some kind of we want to express zeta of 2, 3, and we want to express both zeta of 2, 3 and zeta of 3, 2 in terms of odd zeta values. And in fact, there is this, how do you say, I'm going to say Francis Brown used motivic arguments to show that that zeta of 2, 3. Right, let me write them like this. Red. Zeta of 2, 3 is negative 11 over 2 zeta of 5 plus 3 zeta of 2 zeta of 3, and zeta of 3, 2. We have also, this is negative of, so 9 over 2 zeta of 5 minus 2 zeta of 2 zeta of 3. I think it's, oh my God, it's the same thing. All right, so, so we have these relations, right? Of these, so these are proved by Brown. Like, this is a very deep paper. Proved it. So this was in 2012 paper, Francis Brown, mixed state motives over Z. It was 2012. But this was published in Annals of Mathematics. So as you can see, we can express the two in terms of these. And in fact, you know, you can actually do it. It's enough for you to write down to prove this one here. Sorry about that. So if it's enough for you to prove this one here, if you prove this one here, right, the first one, you can derive the other one from the Stoffel relation, right? Okay. Here we go again. All right, so
yeah,
that's great. Wow. All right, so we have this. We said this linear relations, right? And well, in a way, let me just say in weight 6 what happened. So this was in a weight 5. Then we said there are 6 linearly independent values among these 8 values. But in weight 6, we have the following. So Z6 is generated by these values, zeta of triple zeta of 222 and double zeta of 33. And we will see that there will be a relation between these. In fact, we would like to see how many of them are some kind of a rational multiples of pi to some power. And again, this will confirm the fact that D6 will be less or equal than 2. So as you can see, any way we play, we get the upper bound. But now, if Zagier conjecture is true, let me just say, so if Zagier conjecture, so if Zagier dimension conjecture is true, so we'll get the following. So let's write them in weight 2. So what do we have? We have D2 equals 1. So we have only one value, zeta of 2. In weight 3, we have D3 again equals 1. So we have, again, we have only one value, zeta of 3, right? In weight 4, we have, again, D4 is 1. So we only have these values, zeta of 2, 2. All of them can be expressed in terms of zeta of 2, 2. In weight 5, well, if we want D5 to be 2, we have, this will be generated by these, we have these two values, zeta of 2, 3, and zeta of 3, 2. In weight 6, we'll have D6 will be again 2. So again, just like we said, we have these values 2, 2, 2, triple zeta, and a double zeta of 3, 3. And let me write one more. D7 will be 3. So if we want D7 to be 3, we'll have these 3 values, triple zeta of 2, 2, 3, triple zeta of 2, 3, 2, and triple zeta of 3, 2, 2. So you observe one thing here if you look at it, that all of them are spanned by multiple zeta values. So for a given weight, you see that all of them are spanned by multiple zeta values involving 2s and 3s. And this was, let me go back with history a bit. So this was Hoffman's conjecture back in '97. And proved by Francis Brown in 2012 in the same paper that I just mentioned previously. Basically, the conjecture says the following, that every multiple zeta value can be expressed as a Q-linear combination of multiple zeta values of weight k involving 2s and 3s, right? So in other words, this the algebra of multiple zeta values, right, is spanned or generated by these multiple zeta values with ki's being 2 and 3, with all ki's being either 2 and 3, right? So that was Hoffman conjecture, and was proven by Brown. So and now, just like I said, let's play around with some of these relations, right? In fact, so let's see some identities among multiple zeta values. So I will I'll prove a bunch of them. And maybe, well, I wanted to, like I said, I was very ambitious in proving most of it, but since we lost time with some technical difficulties, I'm just going to prove some of them. And in fact, I will prove Hoffman-Zagier evaluation for zeta of 2, 2, 2, 2, 2. And maybe I'll leave it for next time when I will discuss more about the algebra of the Hoffman algebra of multiple zeta values. I will leave for next time the Dirichlet duality theorem and Broadhurst Zagier evaluation. So in other words, let me just say one thing. So let me just prove this theorem. Let me write this. So theorem, which goes back to Euler, 1776. Well, I want to do it by very elementary, without using any double shuffle regularization, anything like that. In other words, we like to prove that zeta of 1, 2 equals zeta of 3. And there's plenty of ways to prove this. In fact, I would like to introduce the Pauli logarithm for this. So, there are plenty of proofs. In fact, there is a paper, so proof. There is a paper by Borwin and Bradley, I think. They give like 28 proofs for this relation. You see a bunch of techniques. But I want to prove it in a fancy way. I'm not going to prove it the way Euler did it. Euler did it in a very, very tricky way. So he considered the sum. He evaluated the sum in one way. You get the result. Then he evaluated the sum in another way, you get zeta of 3, and then you equate the two. All right, so let us introduce in fact, it's Euler's Pauli logarithm. Which is Li m of z, right? Which is given by this series, z to the m over n to the power m, for values of z, for complex values of z less than 1, right? And clearly, if we differentiate this term by term, so the derivative
Sorry, is z to the n?
Z to the power m, yes. Sorry, to the n. Oh, yes, yes, you're right. To the n, correct. Yes, and that's the correct function, yes. So, and now if we want to differentiate this with respect to z, right? So this is 1 over z times Li m minus 1 of z, right? That's pretty easy to see. So our theorem, so now what we're going to prove is that Euler's relation is equivalent with, so Euler's relation is equivalent with, well, I'm just going to prove it in this way. The sum from n equals 1 to infinity of hn over n squared is 2 zeta of 3, right? This is 2, this sum. Where hn is the harmonic sequence, the harmonic number. Right? So this will be equivalent with Euler's relation. So, like I said, there are plenty of ways to do this, but I'm just going to use Euler's polylogarithm. In fact, let me point out a remark here. For m equals 2, we call this, okay, let me write it here. M equals 2 is the polylogarithm, is the dilogarithm function, which is very, very useful. In fact, there is a survey of an excellent survey of Donzagier regarding the Euler's dilogarithm and its implication, in fact, to hyperbolic three manifolds, algebraic topology, and so on. So it's intimately connected to, to those stuff, and especially even its generalization, the Bloch-Wigner dilogarithm. All right. Well, I don't need to go into details, too many details about this, just the basic stuff. Now, what we're going to do is the following. So we're going to express this guy here, we're going to express it in terms of the some kind of a dilogarithm in combination with trilogarithm, right? So for m equals 3, so let me write here, m equals 3, we deal with the trilogarithm, and so on. This trilogarithm. All right. Okay. So now let's write this. So we write, I don't know, for some reason I feel the screen is so big when I look at it, and it's, and I don't, there is not much room to, so that's why I'm putting everything in one window so that we can have as much information as possible. So we have this, right? And the way I'm going to write this is in the following way. So I'm going to write hn, the harmonic number, as an integral. So I'm just going to leave the denominator, and I'm going to work on the numerator. So this would be the sum from j equals 0 to n minus 1 of the integral from 0 to 1 of t to the power j dt, correct? And now this will be the sum you see here, like we have a geometric series, so this will be nothing else than just the integral from 0 to 1 of 1 minus t to the n over 1 minus t. So this would be, this guy here is, if we want to write this as an integral, we can commute the infinite sum with the integral. So this would be the integral from 0 to 1 of zeta of 2. And now, this guy here, 1 minus t to the n over over 1 minus t. So we can write this as, so this would be the logarithm, right, of t over 1 minus t dt. And now what we're going to do is just integrate by parts. So integration by parts, so an easy integration by parts will give us that this would be, well, and we use this property. So let's keep in mind that when we do it, we use this property. So in the case of the logarithm, and you see, if we have the rank here will just decrease by 1. So the derivative of trilogarithm will be dilogarithm and so on. So this would be, if we apply integration by parts, I hope I'm not mistaken. So this would be zeta of 2 times log of 1 minus t minus 2 trilogarithm of 1 minus t, right? Plus, let's see, what do we have? Oh, 1 minus t plus 2 dilogarithm of 1 minus t log of 1 minus t. Please correct me if I'm making mistakes. Yeah, plus 2 dilogarithm of t times log of 1 minus t, and plus the last one plus log of t times log of squared of 1 minus t from 0 plus to 1 minus, right? And anyway, we put this together, everything. So this is just 2 times the trilogarithm evaluated 1. And of course, this is 2 0. So that's how we prove this. Anyway, like I said, there are plenty of other ways. Well, if you want a little bit more elementary to prove, and you don't need to make use of the dilogarithm or trilogarithm. Yeah, I think there is a way of manipulating the harmonic sequence anyway, but using another integrations. All right. Now let me, so this is one way to prove this. Let me see, let me see. I wanted to do something else as well. Yeah, okay. Another thing that I wanted to discuss is very important. We would like to discuss some, because we have seen just in a particular case for zeta of 2, but since we're dealing with low weight, I want to discuss about general formulas for shuffle. In fact, for double shuffle, for shuffle and double shuffle to be more exact, because we already know about shuffle. For shuffle and double shuffle. Relations. And in fact, what I'm going to do is just I'm going to multiply again two single zeta values. So let me remind you, the shuffle was that if we multiply two single zeta values, zeta of k1 times zeta of k2, this was zeta of k1, k2 double zeta plus zeta of k2, k1 plus zeta of k1 plus k2, right? All right, so that was a shuffle. But the question is there a way to have a similar relation for the shuffle? So in other words, when we multiply the integral representation of the single zeta value, so the question is, do we have a similar relation for the shuffle product? So in other words, can we multiply zeta of k1 or times zeta of k2, but we would like to multiply their integral representation. So the multiplication of their integral representation. But in fact, what is an integral representation, right? We only have seen in the case for zeta of 2. So zeta of 2, let me remind you, is dt1, 1 minus t1, dt2 over t2. But the question is, how does this look like for a general zeta of k? In fact, we can write for zeta of k. Let me just write it. So this will be the integral representation of over 0 less than t1 less than tr less than 1 dt1 over 1 minus t dt2 over t2 dtr over tr. So this is the integral representation for the Riemann zeta value, right? And of course, in the case k equals 2, you'll get exactly the one. But now, imagine if we multiply two single zeta values, right? Zeta of k times zeta of whatever, L. Imagine zeta of maybe R. Wait, zeta of R. So imagine if we multiply some zeta of k, zeta of R times zeta of S, for example. Wow, imagine we have to shuffle all those. It will be crazy to do that. And I don't want to do it. So the thing is how to derive a similar shuffle relation. So we still want to answer the question. And well, we can be rescued in this sense by some, so we have the following theorem. The shuffle relation for single zeta values. So let's see when we multiply these two, what happens. By the way, can you still hear me? I hope everything is okay. Can you hear me well?
Yeah, it's all good.
Okay. So imagine that we multiply their integral representations. So this would be zeta of k1 times zeta of k2. So we'll have the following formula. Hold your breath a bit. And I will prove this next time in a more general setting when I'll discuss the Hoffman algebra. You will see that it can actually be proven. Instead of me writing all this, I will write it in a very compressed way so that the proof will go immediately. So it's the sum from r equals 2 to k1 plus k2 minus 1. And here we'll have this. So we'll have r minus 1 choose k1 minus 1 plus r minus 1 choose k2 minus 1 times, and here I'll have the double zeta values, k1 plus k2 minus r and r. And this relation holds true. So let me just say that k1 and k2 is greater or equal than 2. Right, so, and let's see if we confirm this. And before we go and prove this, in fact, the proof will follow quite easily in a very unexpected way, but very tricky way. So let's do an example. Let's confirm our expectations with the example that we have already dealt with last time. So let's see when k1 equals k2 equals 2. So again, we have two single zeta values, zeta of 2 times zeta of 2. And now let's be careful here. So we will have what? The sum from r equals 2 to 3, right? Well, of r minus 1 choose 1 plus r minus 1 choose 1 right, times zeta of 4 minus r, double zeta, right? All right, and if we write this carefully, okay, so if we write this carefully, this would be what? Okay, let me just write it. So it will be 1 choose 1 plus 1 choose 1 times zeta of 2, 2, right? This is for r equals 2, so we'll have zeta of 2, 2. And we have the other one for r equals 3, so we'll have 3 choose 1 plus 3 choose 1 times zeta of 1, 3. And of course, this will give us 2 zeta of 2, 2 plus 4 zeta of 1, 3, which is exactly what we proved last time when we multiply their integral representation. So you see, this indeed confirms the shuffle product, sorry, in that we talked about, right? And of course, you can play around with this. You can, for example, if you want to multiply zeta of 2 times zeta of 3, maybe you would like to see some relations in weight 5. And you will get some previous relations that we have talked about when we discussed linear relations in weight 5. Let me see. You see something here. So you get pretty much these relations here. Well, some of them, right? But you can play around with these if you want. All right, so let me just give a quick account of the proof of this. So the idea of the proof is the following. So just basically, just like it says in the book, the proof is pretty easy. So the proof, right, is pretty easy. So it relies on the following lemma. And this lemma can be proven by induction, but we can just use by computations. Basically says if I have, let's say, 2 integers greater than 1, then the following equality holds true. So we have that 1 over x to the power I, y to the power j. So this guy is the sum for r equals 1 to I plus j minus 1 of this thing here, r minus 1. You will see where the binomials come from. So r minus 1 choose I minus 1, x plus y to the power r times y to the power a plus j minus r, and plus this the denominator will be the same. And here I'll have r minus 1 choose j minus 1. So I'll have this. So you can prove this by induction. So induction on I and j, right? So you do induction on both of them. And then you just take the sum. So the shuffle relation will follow immediately. All right. So if you look at the shuffle, as you can see, it's not very similar with the Stoffel relation, right? So let me remind you the Stoffel relation. Let me write it here. Maybe I should write it here. Zeta of k1, k2, and zeta of k2. This is zeta of k1, k2, plus zeta of k2, k1, plus zeta of k1 plus k2. So this was the Stoffel relation, right? So this is the Stoffel. And you can combine the two, right? And if we combine these two, So let me write, so combining the stuffle and shuffle, we obtain what we call the double shuffle relation. Double shuffle relation. And of course, we which is given by the following. So this is zeta of K1, K2 plus zeta of K2, K1 plus zeta of K1 plus K2. This is nothing else than just this sum. R minus 1 choose K minus 1 plus R minus 1 choose K2 minus 1 times this double zeta of K1 plus K2 minus R. All right, so this is the double shuffle relation. Of course, you can do the same thing as in the examples we did in the example. You can regularize it. So in other words, you can allow one of the values to be 1, right? And then guess what? You'll get exactly, so by taking K1 to be 1 and K2 to be 2, you'll get exactly, you get Euler's identity. Identity again. Of course, you get, if you plug it in directly, you get to zeta of 2, 1 plus zeta of 3 equals zeta 1, 2. But zeta of 2, 1, since it's divergent, we'll take it out. So we regularize it. So, and then we'll end up with Euler's identity. And then you can play around with these by regularization. You can play around, for example, now, if you want, and actually, I saw this is an exercise in the book. If you have a double zeta value, and then you want to see what is the shuffle of a double zeta value with the single zeta value, that would be actually interesting to see, because in this way we will obtain more relations. All right, so now I would like to say one thing, because I said about the integral representation here. Maybe I just give you a quick account on this one, right? On this one here, right? So zeta of R, how do we prove this? Well, like I said, the proof is quick. So zeta of R is this. dtr with tr, right? Well, the proof is pretty easy. We look at this guy, as you can see here, the first one. We look at this one form here. We look at this one, especially look at this one. This is the sum of t to the m, sorry. So this is just a geometric series. So once we do this, we just integrate over and over again. So let's do it. Let's actually do it. It's a very easy exercise. So once you do it, imagine, so you write this, so this will imply that, let me just write this for 2. So dt1 over 1 minus t1. So this is the integral, pay attention, because it's the iterated integral here. From 0 to t2 of what? Of the sum of t1 to the m, right? dt1. So this would be nothing else than just the sum of t2 to the power m plus 1 over m plus 1. And now guess what? We keep integrating, right? So we proceed integrating out t2, t3, R and integrate out T2, T3, and so on, TR. And then at some point, once we integrate this, so this will imply that this integral in fact, wait, no. This is a series now. So right is this T2 to the power m plus 1 over m plus 1. And this is m greater or equal than 0. And here I have d T2 over T2 and so on, dTr over Tr. And now I'm just going to integrate, and this will give us nothing else than just this sum. 1 over m plus 1 to the power r. Yes. Which is nothing else than zeta over r. Anyway, the proof is pretty easy. Okay. Okay, so we said that in other words, what we call here is that Riemann zeta values. This integral representation just shows you that the Riemann zeta or single zeta values are periods. So this is what we mean by periods. And in fact, there's a much more general theorem by Kontsevich. Let me know. Maybe I'll just say a few words, and probably I will stop because I'm a little bit over time. So there's a theorem much more general by Kontsevich. I think in 97 or 96, I don't recall exactly. He actually observed a much more general phenomenon. In fact, he showed that the multiple zeta values are periods. In fact, let me write it. Are periods. So what does this mean? These mean that we can actually express this multiple zeta values, and I'm just going to write it generically from now on. This integral from 0 to 1, pay attention, this is an iterated integral, and I'm going to write it in this omega 1 times omega 0. This is k1 minus 1 times omega 1 omega 0 kr minus 1 times. So you're wondering who are these two? So this is omega 1 is, in fact, omega 0 is dz over z. So they are one forms. Omega 1 is dz over 1 minus z. So these are the one forms. And of course, this iterated integral converges if so if we have omega E1 times omega ER, this will make sense only for when these EJs are 0 and 1. So this will converge if and only if these indices are 0 or 1, which is this case for multiple zeta values. All right, so this was the theorem of Kontsevich. And in fact, why I'm this is an important theorem because it just doesn't just give you the doesn't just prove you the fact that they're periods or give you the integral representation. In fact, it shows you a much more general phenomenon. And I'm not an expert in algebraic geometry, but these are more for periods of some moduli spaces of genus 0 with n marked points. So you can see these in that context. Well, the proof of this is, well, it's not hard. Again, it uses the proof, and maybe I'll just go with the proof next time in more detail, because because there is another thing I would like to say. I'm just going to mention one thing. So the proof uses multiple polylogarithms this time. So as you can see, as you have seen, we used the polylogarithm, right? Euler's polylogarithm for proving that zeta of 1, 2 is zeta of 3, right? We used dilogarithm, trilogarithm, and so on. We integrated. We've seen the properties, how to differentiate, and so on. Well, the same thing will happen here as well. So we will prove this in the same, pretty much in the same fashion. The only difference is that we will define this multiple polylogarithm function of one variable. Pay attention, because it can be defined of multiple variables as well. And the proof, like I said, goes along the same lines. You just use the derivative of the polylogarithm, multiple polylogarithm in one single variable, and so on. All right. There is one thing I would like to cover, and I think I'm going to stop because I don't want to go too much over time. And I think this deserves there is this theorem of Hoffman and Zeta, which is the simplest one in evaluating multiple zeta values. In fact, there is a story here. They proved it independently. They didn't prove it together. In fact, let me just state the theorem. So if we denote this Hn, this what we call Hoffman family of multiple zeta values, zeta of 2, 2, 2, 2, 2, n times, this is just pi to the power 2n over 2n plus 1 factorial. See, this is actually a pi to the 2n times a rational number as well. It's different from zeta of 2k, right? So it's not the same, but both of them are pi to the 2n times a rational number. In fact, this evaluation was proven independently by Hoffman and Zeta. Hoffman, in his paper, Multiple Harmonic Sums, he gives a very elaborate, I would say, well, analytic combinatorial argument, but Zeta's argument is it's a little bit shorter. And in fact, this is the first family of the simplest family of multiple zeta values for a Hoffman basis. Because if I go back, you see, let me go back a bit. When we let me go back to the dimension conjecture of Zeta. If you look here, you see you have the simplest families. You have 2s and 3s, but you also have only 2s, right? For example, in weight 2, you have zeta of 2. In weight 4, you have zeta of 2, 2. In weight 6, you have, again, triple zeta of 2, right? But you also have double zeta of 3. So it would be nice if we can actually get write down a formula for these values. So that's why I was saying that this is the simplest family of Hoffman family of multiple zeta values. And in fact, let me just maybe I should. All right, maybe I should stop here, and maybe I'll prove it next time, and maybe I'll prove more identities next time. I don't want to go too much into much overtime, so I think I've went overtime a little bit. All right, so I think I'm going to stop here, if that's okay with you.
Great, thank you.
Thanks a lot. So how do I stop the share? Let's see. Do you guys have any questions?
Hey, Cezar. I have a question.
Yes.
You just mentioned Brown has proved an identity with motivic arguments. So can we prove some other maybe elementary method to show the identities?
You mean the for in weight 5, right?
Yeah.
Yes. You mean these two relations, right? Yeah. This. Yes. There is an elementary proof actually for this, because for this family, for example, if you prove this, right, then you don't have any problems with the second one, right? Because from the Stoffel you can recover the second relation. But yes, there you can prove it elementary. There is an elementary way of doing this. And in fact, maybe I should have mentioned a bit, but I didn't want to go over time because the idea, well, actually, it's I can show you my paper, in fact, because I proved this in a much more general. So it's Zeta of 2223. And in fact, it comes from even a more general formula from Zagia's formula, right? So, but you can do it in an elementary way, let's say Euler style way, by just expressing, for example, I can write it, why not? So look, for example, you can express, let's say, zeta of 3. Oh, like, let me take the Euler's identity. In fact, I wanted to prove this, but I skipped it. Zeta, you can express this as the rational zeta series, right? So this is our rational zeta series. So this is the simplest one, proven by Euler. But this can be a finite Q-linear combination of odd zeta values. And in fact, in our case, will be something like, this one here, right? It's actually, wait, let me be more specific. This is a rational zeta series. But what if I want to do the same thing for zeta of 2, 3? What if I want to write this as a rational zeta series? Does it make sense what I'm saying? So I'm writing this as a rational zeta series, just like with this one for zeta of 3. And then I can express that rational zeta series as a Q-linear combination of odd zeta values, maybe zeta of 3 and zeta of 5, which can be indeed done. And the coefficients are exactly this. But they actually, yes, it can be done elementary.
Okay, thanks. I realize that it's a special case of the Laguerre's work.
Yes.
In 2000. I really want to ask. So my question is that, is there any known identity which is not proved by elementary method? Does you know such example?
Like not proven analytically, and there are plenty of them which we don't even know a formula. For example, what if I go in weight 6, zeta of 2, 4, zeta of 4, 2? I mean, they can be expressed in some ways, but a much more general formula, for example, zeta of 2, 2, 2, 4 in weight 6. So if we go, let's say, more general Zagier formula, that's not known at this point. And there are other identities as well, but they're not, I would say, they're not too many proven. I mean, there are infinitely many identities you can come up with these things.
Okay, thanks.
But they're very hard to prove. For example, next time, in fact, next time I'll dwell more on proving identities for general multiple zeta values. And you will see there is this Broadhurst identity of just involving zeta of 1, 3, 1, 3 you can prove it elementary by using hypergeometric special functions, whatever. But the proof is very tricky. And in fact, maybe next time I'll dwell more on proving identities of this type, so that in general, for general multiple zeta values, not just for in low weight.
Okay, thanks.
So if there are other questions.
Yeah, if no